Hello everyone. Today I'm gonna talk about a theorem of Fermat, and this is the theorem. So basically it says a prime can be written as the sum of square of two integers if and only if it is congruent to 1 mod 4. So why am I interested in this theorem? This is my personal opinion, is I studied class field theory actually for 2 semesters, but I still don't feel like I understand it. And then today I want to go back to the fundamentals, and I want to understand it by examples. And it turns out, it feels like from the reading, that this theorem of Fermat is the beginning of class field theory. And I really want to know an elementary proof, and I found one in a book, I think called Primes of the Form n square, primes of the form x squared plus ny squared by David Cox. And I found a proof of the theorem I just mentioned on page 8 through 11. So I'm gonna talk about the proof. Obviously, I will not go into details, but okay. So first I want to say one direction of the theorem is obvious. If P is odd prime that can be written as x squared plus y squared, then it is obvious P is congruent to 1 mod 4. It might take you 2 to 5 minutes to think about it, but it is really obvious. And then we want to prove the other direction. And again, I'm just summarizing what I read from the book, and you can find the detailed proof from the book I just mentioned. And this is the first step of the proof from the book. First, if P is a prime is congruent to 1 mod 4, then P is a divisor of x squared plus y squared for integers x and y, and x and y do not have common denominators. And okay, so I'm gonna prove this first. So we first prove P is a factor of x squared plus y squared before we prove P is actually equal to x squared plus y squared. And the proof goes like this. So it uses some group theory and field theory. So you need to know what a group is and what a field is. And the proof goes like this. So first, look at the polynomial x squared plus 1. And this polynomial has a solution in the field z mod p. And this fact used the sum group theory and field theory. And suppose that we proved that, then it means P divides x squared plus 1 for some integer x. So this proves the previous statement. It proves that because here y is just 1. So basically we say P divides x squared plus 1 squared for some x in Z, and x and 1 are obviously co-prime with each other. Okay, so this finished the proof of this part. Now let's go to the next part. The next part says, well, if you have P divides x squared plus y squared, then the prime P is equal to a squared plus b squared for some integers a and b. and that proves the theorem of Fermat. So now I'm going to prove this part. Well, this part is a bit harder, but the method it uses is called descent. And the key to prove this part, the key to actually form a descent is actually by observing we have a equality of any numbers. Of course, here A, B, C, D are integers that we are focused on. So this very simple equality is the key to start our descent. So I will just say it is a squared plus b squared times c squared plus d squared equals the sum of two squares. So if you look at this equation, and you think, if you look at this equation and you think, okay, so on the right side, I don't know whether it is like a right or left when you watch this video, but for me, it's like on the right side, you have the sum of square of two integers. And if you think the first one is x, the second one is y, and then you have x squared plus y squared can be written as the product of another square sums. And now imagine that if p is a divisor of the x squared plus y squared, then as a prime p, it has to be the divisor of one of the factors. It means p divides, let's say, a squared plus b squared, but it is a smaller sum of squares. So this means that if p is not, this means that if p is not equal to x squared plus y squared, then p will be a divisor of a smaller sum of squares. And this process cannot continue infinitely. It has to stop at a certain point. P is equal to a squared plus b squared. So that's the idea. That's not a proof, but that's the idea how this is done. And if you go back and watch what I previously talked about, we actually already proved. I already mentioned the whole proof. Talked about the whole proof of the theorem of Fermat.